just quickly about what Flexitricity do to put this into context. We're a demand response aggregator, so we offer flexibility services to National Grid, so in the electricity market. So I'm going to be talking about how heat networks can play a role in balancing the electricity system. And to start that, I'm going to give you some context about the way that the electricity system is changing and what kind of challenges that's bringing for National Grid, just because I know that this is more of a heat audience. So I thought I'd start with some basics. So the electricity system has changed significantly in the last 15 to 20 years. Particularly, we have a lot more electricity coming from renewables, which aren't always generating when we want them to. And then also a lot of our large, sort of clunky baseload is coming off, with a lot of the coal coming off in 2025, and then also the sort of rocky future of nuclear energy. And at the same time, the way we consume electricity has also changed significantly because our appliances and lighting are much more efficient, and that's really changed the shape and size of the peak, the electricity peak during the day. And then also with EVs becoming more and more popular, that's also completely going to change the way that we consume electricity and the shape of the demand that National Grid has to deal with. And so because of that, we keep breaking electricity records. So I've put up some from 2018, but almost all of these, except the coal one, I think, were broken in 2020, I'm sure I got rid of that. Were broken in 2017 already. And so you can see there's a lot less coal in the system, a lot more solar generation, especially in the summer. And then, I'm really sorry about that. Right. But I'm mainly bringing these up because it kind of gives you an idea of how the electricity system is changing and what kind of problems that's causing for National Grid and how it's becoming more and more difficult to actually balance the system. So here's an actual slide from National Grid. These are 3 consecutive days in January 2017, and what they're showing you is the electricity demand profile. And you can see the 25th down there, the 24th, and then the 26th up top. And that big swing there is actually solar generation, because solar generation, when it comes onto the electricity system, looks like negative demand. It doesn't look like generation because it's connected on the demand side. It's usually on people's roofs or other buildings. And that 8 gigawatts of solar I was talking about in the last slide can have a huge effect on the system, because when it gets sunny in the middle of the day, it looks like demand has just completely dropped off, but actually what's happened is all of the solar generation has come on. And that causes real problems for National Grid, because this is just one day to the next. They have to be able to deal with 8 gigawatts of solar coming on that might not have come on yesterday because of cloud cover. Because National Grid's main job is balancing the electricity system, which means always keeping supply and demand equal. And the way they usually do this is with large power stations, which take several hours to warm up. And so if a interconnector or another large power station trips, I'm sorry guys. If an interconnector or another large power station trips, you can have the issue that National Grid are going to need a lot of electricity very quickly, and power stations can't turn up in that kind of time frame. And so instead of running the system most efficiently, which would be to run exactly as many power stations as you need to meet demand, they run more power stations and keep them at part load and sort of tweak them up and down, because that's much quicker. But that does mean that they're not particularly efficient, which is actually also means that they're got a lot more carbon as well. So there's actually like a carbon cost to keeping all these generators at part load to manage the system. And this is how the system has been traditionally managed. But that's kind of changing. And what does this have to do with heat networks? So currently heat networks make about 2% of UK heat demand, but there's a possibility of going up to 17% in the future. And at the moment it's mostly natural gas boilers, but there is a big room to expand to CHPs and heat pumps, which is what's particularly interesting to people like me who are interested in demand-side solutions to National Grid's electricity balancing issues, because those are both huge electrical loads. Because what you can do is turn on a heat pump in the middle of the day that wasn't already running, and put that heat into the network if there's a day where there's too much solar on the system. And heat networks in particular, rather than just a heat pump on its own or a CHP on its own, are particularly interesting because the network itself is flexible. There's a lot of thermal inertia in the network, and then when you add a heat store, you get even more thermal inertia, so you can actually flex the system without actually affecting the heat that's delivered to customers. So you can use a heat pump, or you could use a CHP, which is what's happening at Gateshead Energy Center. They've been working with Flexitricity, providing electricity balancing services to National Grid since 2016. And last October, they became the first INC customer to offer electrical flexibility to National Grid in the balancing mechanism. The balancing mechanism is the main way that National Grid balances the electricity system. So being able to compete directly with those large generators is really important for making this a viable and useful service to National Grid. So what happens at Gateshead Energy Center is they have two 2-megawatt CHPs, and they run them for the heat load of the network. So it usually means during this time of year, because it's been a bit unseasonably warm, one CHP is running for the heat load, and the other one is on standby in case the heat load changes or the heat in the store drops. That second engine at the moment is being instructed up by National Grid to turn on when it wasn't going to be. The heat is then put into the system to be used later. But the electricity is helping balance the system, and it's an alternative to keeping more and more power stations at this sort of inefficient part load, or in the case of turning off the CHP, which they can also do, the CHP that's running on duty, they can turn that off for 20 minutes to an hour and let the system coast on its thermal inertia so that the customers don't notice anything, but instead of generating electricity and putting it out into the system, they're absorbing the electricity that would otherwise be being curtailed from a wind farm or other bits of the system. So the reason that heat networks like Gateshead are so interesting is because it's the network itself that's important rather than what you're putting into it, because you can change that over time as the system changes. So I think we're going to go from a system at the moment where the heat network, you put it in, and then the input is actually going to change over the lifetime of the system, because our demands, both in heat and electricity, are changing significantly and will change significantly. But then also the demands on the system as a whole are changing significantly, and this really gives heat networks a real future place in the electricity and energy system as a whole, because they can provide the same kind of service as a battery, if you think about it. Because if you have a heat pump or a CHP, you can flex when it's going to run and offer that to National Grid, and at the same time provide heat to customers. So it's a real interesting way to provide heat to a wider network and do what you were going to be doing anyway, but then also help balance the system in the future. So it means that we have to have less large power stations, and we can integrate more renewables into our system. All right, and that is me.